Welcome back to Calculus AB. You guys have survived semester 1 on to conquer semester 2. I find that this semester is both a little shorter because we need to be done by May and there's spring break in there. And it's a little bit easier because most of this semester is going to be about working backwards. The first semester, of course, we took derivatives. The second semester is going to be, if you have a derivative, how do you work backwards? And since we already know all of our derivative rules, that makes a bunch of the topics we cover this semester a little bit more straightforward. So, speaking of working backwards, let's take a look at that opener. We're going to find, or you're going to find, two functions that are called f of x, whose derivative, f prime of x, equals 3x squared. So that means when you take the derivative of whatever this function is, your derivative better be equal to 3x squared. And it's asking you to find two different functions whose derivative equals 3x squared. Maybe they're two different functions, maybe there aren't, but go ahead, pause this video for about 30 seconds, see if you can figure out functions where when you take the derivative the answer is 3x squared, and then unpause and we'll chat. Okay, well, hopefully you've tried that, and I imagine many of you came up with the answer that I see every year, which is you found that f of x could equal x cubed. And hopefully by looking at that, you see that the derivative of x cubed, and I hope you haven't forgotten this over winter break, is 3x squared. Nothing too shocking there. But the tricky part is, did anyone come up with a second function? Because there is actually a second function. There's actually more than one. And if you did, nice job. I bet you found something that looks like this. How about x cubed plus 5? Because, of course, the derivative of that, derivative of x cubed is 3x squared, and plus 5 becomes plus 0, which is just 3x squared. And so you might start thinking, well, wait, is that other function, or is this answer unique? And I think it's not, because instead of plus 5, we could have, of course, done minus 10 or plus a million, anything like that. Now, what does this all mean? How does this relate to first semester? Well, let's start with a little bit of vocabulary. So sometimes you'll see this question that I asked you on the opener phrased as, given f of x equals something, then what is capital F of x? Now, on the opener, of course, I said you are given f prime what is lowercase f of x. But if you wanted to ignore that prime notation and phrase this in a separate way, then you might see this as given lowercase f of x, then what is capital F? And capital F of x is known as the antiderivative of f of x. So that's really the same thing that we did here. We could say if you have f prime, then the antiderivative is f of x. But oftentimes, instead of starting with f prime, we like to start with f of x. And it should make sense that there's a step above f of x as well, right? You could even think of this as if we have f of x in our order here, and we wanted to take the derivative, so we wanted to find d dx of f of x, that would of course bring us to f prime of x, and then we could take the derivative again to bring us to f double prime of x. Well, then that is of course moving maybe down this ladder. We could also move the other way, and we don't have a symbol yet of how to move the other way. We'll see that in a bit, but f double prime, the antiderivative would be f prime. From f prime, the antiderivative is f of x. And then, of course, from f of x, the antiderivative would be capital F of x. And, of course, all of our derivative rules are the same, but now we're working in reverse, and maybe that will throw off some of those rules. So going back to this, capital F of x is usually, instead of phrased as find the antiderivative of, it actually means find an antiderivative of f of x, and this should be a lowercase here. Okay, and the difference between an versus the is illustrated in the opener that you did up above, right? Find an antiderivative of capital F of x. Well, there are, of course, a couple different answers. You could have said that if you wanted to find an antiderivative, it could, of course, be, and actually this one's a little bit trickier, so we're going to try the antiderivative of x cubed. Well, we know we're going to have to add 1 to the power, so that's got to be x to the 4th, because when you take the derivative, the power always reduces by 1. But if I wanted to check that, if I wanted to find the derivative of f of x, capital F, then this would become 4x cubed. I don't see a 4 over here, though. That's a bummer. So we might have to find something to offset this new power of 4. So can you think of something that when you take the derivative, when the 4 comes down, will cancel out a 4? And this brings us really back to Algebra 1, to our knowledge of reciprocals. I think if we put 1/4 x to the 4th here, then we would be good to go. Right? And as a heads up, your textbook would probably not write the answer like this. Textbook writers try to be as efficient as possible, and efficiency means the fewest number of keystrokes, the least amount of space taken up. So instead of that, they would think of this as over 1, they'd multiply, and they'd write that as x to the 4th divided by 4. I'm much more fond of this as an answer. Your textbook prefers this. It is totally up to you. Right? Now, if they wanted to do something like this, and they said, well, here, now we have the derivative equals x cubed, we want you to find f of x, lowercase f of x in this case, well, you could put the exact same answer, couldn't you? You could say it's 1/4 x to the 4th, or x to the 4th over 4. If you wanted to be really wild, you could put an extra constant at the end, like +5 again, or +6 or +7, whatever sounds good to you. But this is really just to illustrate the difference, or rather the similarities, going from lowercase f to capital F, or from f prime to lowercase f. It's the same idea, just you're in a different spot on that ladder. Alrighty. Now, based on the opener, and of course the example above, you should be convinced that there is not one unique antiderivative for a function. And that has to do with the fact that if you have a constant at the end, the derivative of a constant is always 0. So you could have any constant you wanted. So when you're asked to find the antiderivative, do you just get to pick whatever constant you want, including this +0 we have here? And of course the answer is no, you don't. We actually have a different way to represent all of the antiderivatives. It's kind of a generic, a general form, not a specific single equation. And the way we do it is we say, well, the antiderivative of x cubed is 1/4 x to the 4th. But then at the end, we don't put a 6 or a 0 or whatever. We just put a capital C, where you can think of C standing for a constant. And so we do actually have to put that plus C for any antiderivative in this case. It's not optional. If you forget to put the plus C, and this is a free response question on the AP exam, you automatically lose a point. Kind of a big deal. Now, there is a formula for antiderivatives, but it really, I find almost every student doesn't use the formula. I think if you logic your way through this and have a good understanding of derivatives, you'll be just fine. So why don't you guys go ahead and try a few antiderivatives on your own. If you want the formula for antiderivatives, you can check in Chapter 5 in your book, but I think, again, you'll be all right here. So try A, B, and C, and then we will talk about the answers and go a little bit more into notation once you unpause. Alrighty, let's see how we did here. This first one I think is probably not too bad. When we take the antiderivative, or when we find the antiderivative of f prime of x equals x to the 5th, then we should find that f of x equals 1/6 x to the 6th power. The 6th will cancel out the 1/6 when we're checking that derivative, but we of course can't forget that plus c. Alright, what about 3x cubed? Now, this one's a little bit more difficult, and so there's a couple ways to think about this. Some people might go through and say, well, I know it's x to the 4th. We can put that plus c in there. And then they're thinking, well, 4 times what gives us 3? That's maybe a slightly harder question, and some of you have a very good knowledge of fractions or decimals, and you're like, no, I got this. However, we need to remember a rule about derivatives that also holds true with these antiderivatives, and that is if there's a constant out front that's multiplying or dividing, it does not affect the derivative, and the same is true for the antiderivative. So what I like to do is, if I'm going to go ahead and take this antiderivative here, and my eraser is deciding not to work, very exciting. I'm, instead of taking the antiderivative of 3x cubed, I'm going to move the 3 out front and just say, okay, let's ignore that 3 and just focus on the antiderivative of x cubed. And that is, of course, x to the 4th. And then, we did this earlier, we need a 1/4 in front, because the 4 will cancel out the 1/4, and then we'll just leave us with that x cubed. Of course, not forgetting our plus c at the end. Once you've done that, then putting this together is a lot easier. And we come up with what many of you, I'm sure, came up with, 3/4 x to the 4th plus c. Easy to check. Derivative, 4 comes down, cancels, leaves you with 3. So let's try one more, and I think you'll see that that method isn't too terrible. Now they gave us the second derivative, and they want the first derivative, but that's just an antiderivative. Same type of question every time. And I'm going to do that same trick. I'll factor out that 2/3, and we're just going to take the antiderivative of x to the 4th. We have to increase the power by 1, and a fraction in front to offset our new power. Putting this all together and multiplying straight across, 2/15 x to the 5th plus c. Nothing bad at all. Now, it is a little bit cumbersome to write out that full sentence that I've been doing up above, like given f prime of x equals this, then what does f of x equal? And so it would be nice if we had a symbol kind of like that ddx symbol from earlier, where ddx means take the derivative. Is there a way that we can tell someone to take the antiderivative? And unfortunately, it's not ddx just flipped over. That would actually get a little too confusing. So we're going to have a quick talk about notation first, and then we'll introduce the symbol that means to take the antiderivative, or rather the collection of symbols. So it's not a surprise that we've seen y prime as, I don't know, as synonymous with f prime or f prime of x, right? Non-function notation, function notation, nothing too bad. And we know that if we start with an equation like y prime, let's put out a function of x here, let's just do an easy one of 2x, then if we work backwards, if we find an equation for the antiderivative, it becomes y equals x squared plus c. So we started here, and we ended with y equals just a function of x. We also need to be comfortable with the fact that y prime is the same as dy dx. So I'm really just rewriting both of these here. Now, if we treat dy dx as a fraction, and I think true mathematicians will probably cringe at this step, but I think it does a nice job of showing what we're going to see on the next page. If we treat this as a fraction, then shouldn't we be allowed to multiply both sides by dx? And that gives us dy equals f prime of x times dx. And we can, of course, always put that invisible value that's multiplying by this dy out front. Now, one thing we haven't done is discuss what are these dy's and dx's actually doing. We know as a whole this represents the derivative, but later on in this unit we are going to actually discuss what the dy's and dx's do, why they're there, what they're actually called. For now, though, I think it's enough to just convince you that we could rewrite this like so. All right. What we're going to treat dy and dx as for now is just with respect to y and with respect to x, right? d dx means with respect to x, d dy means with respect to y. So that helps us when we're taking that antiderivative, right? So if I wanted to take the antiderivative of 1 with respect to y, then the antiderivative of that would be y, because d dy would be 1. And then if I told you to take the antiderivative of f prime of x with respect to x, you would say it's f of x. And then, of course, we put the cute little plus c over here. All right, nothing too terrible. Now, if we start here and we wanted a symbol to say take the antiderivative of each side, then we do have a way to do that. Instead of me writing find the antiderivative, we use this cool little squiggly snake kind of elongated S-looking thing that looks like this. This symbol, this antiderivative symbol, is going to tell us to take the antiderivative of this interior function with respect to whatever is at the end. So take the antiderivative of 1 with respect to y. The antiderivative of 1 is y. And same thing over here. The antiderivative of f prime of x with respect to x is f of x. And we do, of course, need a plus c at the end. Now you'll notice then that this antiderivative setup actually has two parts to it. It has this little squiggly symbol that we'll give a name to in just a second, and it also has a dy or dx or d whatever the variable is at the end. And you do need both of those. Very important to get both of those. So let's get a little bit more technical in our definitions. This squiggly s thing over here is known as an indefinite integral sign. All right? It means take the integral of, or find the antiderivative, or find an antiderivative of whatever's there. Indefinite, so it's known as an indefinite integral. There are definite integrals that we'll see later on. It's an indefinite integral because we're going to get an equation as an answer. Definite integrals will give us a value as an answer, but we don't really know what those values mean right now. We'll come back to that. Okay? What else do we have? Well, this dx, at least for now, we're going to treat as with respect to x. It does mean a little bit more, and there's a bunch of history rolled into that. Technically, it's known as a differential, but we're going to give you a few days to practice our antiderivatives before we get really technical with that. You do need to realize that whenever you do the antiderivative, you need both parts, and you can really think of them as like parentheses around whatever function is on the inside. Some people say, well, do we need to put parentheses? Sure, you can. At times I do, at times I don't. You don't have to, though, because readers will see both of these and say, oh, this is where the antiderivative equation starts, this is where the antiderivative equation ends. And then, last but not least, f of x, which is your actual equation you're finding the antiderivative of, is known as the integrand. So we have an integral, integrand. And it's the function, of course, for which you're trying to find the antiderivative. So the rest of today, really 1, 2, 3, 4, 5, 6 questions, just has you practice taking a few antiderivatives, and your independent practice will do the same. I'm going to suggest that instead of trying all 6, you try one, make sure you're right, try another, make sure you're right, because they're generally designed to increase in difficulty, and the last 2 or 3 in particular are quite challenging. And then at the very end, we have a couple important dates to go through, and that's it. So here we go. Go ahead and try that first one. Unpause when you're ready. All right, hopefully you didn't struggle too much here. We're looking for the antiderivative of 3x squared, and the antiderivative of 3x squared is going to be x cubed. 3 comes down. I always check that in my mind, plus c. Right? I really do think it's a good idea to check everything. Okay, the derivative of that, that's 3x squared. C is a constant, 0. Great. Okay, then this matches. Woo, we're doing well. All right, go ahead and pause. Try that second one. All right, this one is a little bit more challenging here, a little bit more challenging. I'm going to change colors. Let's do the answers in green, I think. There we go. Okay, so a little bit more challenging. I'm going to leave that 3 out front, and then we're going to say, well, the x becomes x squared. To cancel out a 2, we need a 1/2. And so putting all of this together should give us 3/2 x squared plus c. I would encourage you to start trying to go from the antiderivative, from the integral, over to this and skip this middle step. You can start working it out in your head and say, oh, I know the 3 is going to be on top, 2 needs to cancel, so on and so forth. But if you're not there yet, and that's totally okay, definitely use this nice little trick to get us to the answer. And of course, I'm going to check my answer, always important. And to check our answer, the 2 is going to come down and cancel out the 2. That's just going to leave us with a 3, x to the first plus 0. Yes, we've done it. This matches our integrand on the interior of the integral. All right, pausing again. Go ahead and try another. This is really just putting everything together, and I don't think it's, again, too terrible. We're just going to do it in each piece, just like with derivatives, where if our certain terms are separated by addition or subtraction, you can do each derivative separately. Antiderivatives work the same. The antiderivative of x becomes x squared with a 1/2 to cancel out the 2, minus antiderivative of 3. And I see a lot of people mess this up. They're like, oh, isn't that 0? No, the derivative of 3 is 0. The antiderivative of 3, I think, will be 3x. Right? The derivative of 3x will be 3, and then plus c. Quick check. 1/2 x squared, the 2 comes down, cancels, leaves us with 1x. Negative 3x is negative 3. C becomes 0. We don't really need the 1. There we go. Nice. Okay, next one. this one might have thrown you a little bit more for a loop. And I'm actually going to be writing different answers here, and then I'm going to cross them out if they're wrong. I'll leave them all up here, and I'll probably put the final answer over at the end. So let's look at a couple possible answers that I see over the years. One of them is you just go piece by piece. You say, ooh, x to the 2/3, that's a little bit trickier. We're going to have to add 1 to the power. So let's see, 2/3 plus 1 whole, that's going to be, maybe I'll even do it up here. It's going to be 2/3 plus a whole, 2/3 plus 3/3. You guys are going to get really good at fractions at some point. That's 5/3. Awesome. And then to cancel out 5/3, oof, trickier. What about 3/5, right? That's the reciprocal. And when you multiply 3/5 and 5/3, they cancel. That's good. Then you say, okay, the antiderivative of x, we just did that one. That's 1/2 x squared plus c. Whew, gnarly. However, don't we need to check that answer? So to check that answer, we say, okay, we need to take the derivative of all of this. But wait, we have two functions, each one containing x multiplying together. To take the derivative, wouldn't we need to use the product rule? And I don't want to do the product rule of that. There's going to be a plus in the middle. Things are going to get wild. But I'm very confident, especially because of that plus in the middle, that it's not going to equal what we want it to equal. And so in this case, it looks like our antiderivative and derivative rules have a little bit of a hiccup. Now, one thing you might have been pondering as you came up is you might have said, well, wait, x to the 2/3 is multiplying times x. So, and I put a little times here. Technically, there's a times here. You don't have to do that. It's up to you. Whatever sounds good. So you might be saying, well, wait, for derivatives, we'd have to use a product rule. So for antiderivatives, for integrals, wouldn't we have to use a product rule as well? And you're right. However, if you figure out the product rule that you need to use, if you could inform some of those really famous mathematicians, I think they exist, that would be great, because as far as I know, there is no product rule for antiderivatives, which is a real bummer. In fact, there are going to be many functions for which we can't even find an algebraic antiderivative. It's just not possible. So unlike with derivatives, where you can find the derivative of pretty much any function ever, we learned all the rules last semester, antiderivatives, because they don't have a product rule and by corollary a quotient rule, there are going to be some of these where we just can't do. Now in this case, we can actually perform the or find the antiderivative of this one here. But you're really going to have to keep in mind, anytime you see multiplication or division, looking down to the next problem, you are not able to take the antiderivative until you manipulate the problem and find a way to write it without multiplication or division of terms containing x's. So what do we do here? Well, we remember back to Algebra 1. And in particular, we have two of the same base, which means we do something with those exponents, I think, right? When you have the same base, you can add your exponents together. And we already did 2/3 plus 1, right? That's 5/3, isn't it? Okay. And then, so we didn't do any calculus here. This is just algebra review. Now we can do that antiderivative. So the antiderivative of 5/3, add 1 to the power of 3/3, that's going to be 8/3. To cancel out 8/3, I think we need 3/8 plus c. There we go. Now we're good. And I'm pretty confident that if you looked at this and thought that that was the antiderivative right away, that you might think you're crazy, because they definitely don't look the same. But by using those algebraic manipulations, we can find that antiderivative. And if you want to check your derivative, it's a little bit trickier, and I think there's probably no reason for me to go through it. These will cancel, subtract 1 from the power, and then you have to split this apart. So it's kind of a weird one. But having that in your arsenal, why don't you guys go ahead and try problem 5. Hopefully on problem 5, now that you've attempted it, you realize that we have the same situation as before. We have one function containing x being divided by another function. If this was a derivative, we'd have to use the quotient rule. It's not, which means we're in a bit of a bind. Of course, old Mr. Grant wouldn't have given you a problem that you couldn't actually do, would he? Well, I certainly would. However, I did not this time. You can figure out this problem. And again, it goes back to algebra. There are a few ways to tackle this problem, and we saw this in first semester as well. I'm going to go ahead and show you both ways maybe down below before we actually do it. So The two methods we can deal with this are taking x squared, dividing it by the common denominator, and taking 4 and dividing it by the common denominator. And then remembering that we subtract exponents when they're over here, right? 2 minus 5 is negative 3, so I think that's going to become 1 over x cubed. You could have also thought of it as the numerator being x times x and the denominator having 5 of those x's, right? You cross them off, 1 over x cubed. And then this guy is still 4 divided by x to the 5th. Still don't like that division though, so I'm going to rewrite this one more time. How about we bring the x cubed up, and we also bring the x to the 5th up, of course changing their signs. This has no more division nor multiplication of terms containing x's, so we can take the antiderivative of each piece. There is a second way though that appeals to some students, and that is by rewriting this x squared minus 4. Instead of being divided by x to the 5th, we could write it as being multiplied by x to the negative 5th by taking this guy and moving it up. That is allowed. However, we need to make sure the entire numerator is being multiplied by that x to the negative 5th, and then we distribute inside. Same base, so we add the exponents. 2 minus 5 is negative 3. 4 just gets that x to the negative 5th hanging out at the end because there's nothing to multiply, and therefore we have the same answer. So how do we do this? Well, let's go ahead and rewrite it. We know we're rewriting this as x to the negative 3rd minus 4x to the negative 5th dx. And again, you don't need parentheses, but you can if it makes you feel better. And now we do our antiderivatives. Adding 1 to the negative power is probably the second leading cause of incorrect answers that I see here. If you add 1 to negative 3, don't know why I put another integral symbol. If you add 1 to negative 3, you get negative 2. What cancels out a negative 2? Not just a 1/2, because negative 2 times 1/2 would be negative x to the negative 3rd. We need an extra negative there. Minus 4, and then I'll do that same trick I've been doing. Add 1 to the power becomes negative 4, and then we need a negative 1/4 in front, and of course a plus c. Cleaning this up just a little bit more, negative 1/2 x to the negative 2nd. You might notice that this negative 1/4 and negative 4 make a positive 1, which means I don't need to write them. It just becomes plus x to the negative 4th plus c. And you might have been able to see that from the very beginning. You might have been able to see that this antiderivative is that guy. All right, that one was definitely a bit time-consuming. The last one, even though it looks scarier, is not as time-consuming. Oh, and some people might say, well, wait, do we need to rewrite these x's as 1 over x squared and 1 over x to the 4th? Generally, no. You can if you'd like, and maybe the back of the textbook will. I doubt it. But if you want to, cool, but that is the answer. And if you manipulate this using algebra to rewrite it as a different answer, it's still a correct answer, but nobody is going to care one way or another. So last problem for the day, go ahead and try that problem 6, and then unpause when you're ready. Alrighty, so for this guy, I think we're probably going to need a bit of algebra at the beginning as well to rewrite this. We have this 3, and instead of the cube root of x, maybe we rewrite that cube root as a 1/3 power, right? I find a lot of students remember the 1/2 power as square root, so 1/3 should make sense as a cube root. I'm not going to change anything else though. Plus 6 dx, looking all right. And now we just have constants in front, so we can just find the antiderivative, and we should be good. So antiderivative of our first one, we'll leave the 3 out here, and x to the 1/3 power, we increase by 1, 4/3, right? 1 is 3/3. And then to cancel out 4/3, we need 3/4. Next part, minus 4 is again just going to hang out front, and we do the antiderivative of x to the negative 1/3, always tricky here. Add 3 over 3, that gives us 2/3 with a 3/2 to offset the 2/3. And this one's not bad at all. Antiderivative of 6 is 6x. And of course, we would never forget the plus c. You'll see a lot of memes out there about forgetting plus c. It's a nice little running joke where we generally know what it is, but because there's nothing in the original problem, a lot of times we forget that there can be a constant at the end. Should we clean this up? Yeah, probably at least a little bit. We end up with 9/4. You could rewrite this. I probably will not. It's a little bit there are fewer character strokes to leave it as an exponent as opposed to writing it as a radical, right? Cube root of x to the fourth. But if it makes you happy, you can. 4 divided by 2 is 2. 2 times 3 is 6. And nothing else to do at the end. All right. We have done some good antiderivatives of both polynomials and radical and even some rational functions here. We didn't do any trig functions. We didn't do any e to the x, any log. We call those transcendental functions. We'll see those next class. For now, though, I think you have enough to get you through your independent practice. There is a last page on here, but we're going to talk about this as we meet in person or virtually in person, and these will change year to year, so I think there's probably no real reason to take up more time on this video. So hopefully you don't find this too intimidating. If you do, please ask questions. You'll practice this every day, but as long as you have an okay grasp on your derivatives from last semester, then I think this will not be too scary. I'm excited to have you guys back for day 63 when we can practice some of those trig antiderivatives. And for now, go ahead and get to that independent practice, and I'll see you next class.